Welcome to this video. Today, we are going to establish a curious relationship between combinatorics and a certain triangle. Let's start with forming the Pascal's triangle. Start by writing 1 on a piece of paper. On the left and right of this one, imagine that there are imaginary zeros. Now, we form the next row by adding any two of these terms. For example, 0 plus 1 is 1 and 1 plus 0 is 1. And then again we write these imaginary zeros to the side, and we form the next row. 0 plus 1 is 1, 1 plus 1 is 2, and 1 plus 0 is 1. Now, I won't be writing the zeros anymore, but you can imagine them. So, the next row. 1 plus 0 is 1, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 0 is 1. Same thing, 1 plus 3 is 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on.
If we zoom out, we notice that this figure will form a triangle. Therefore, we call this figure Pascal's triangle, after the person who popularized it. Now, let's take a look at what happens if we expand a term such as x plus y whole thing squared. With power 2, you will get x squared plus 2xy plus y squared. With power 3, you'll get this. And with power 4, you'll get this. Let's do some more powers, including the ones before 2. Now, let's take a closer look at these coefficients. What do you notice about them? Precisely, it's exactly the same as the Pascal's triangle. Isn't that interesting? In the first video, which we highly recommend you watch if you're unfamiliar with combinatorics, we talked about how combinatorics must necessarily appear in the binomial theorem. With this knowledge, we can safely say that Pascal's triangle can be written as a long list of combinatoric terms. The lines across here represent the different values of n in n choose k, and taking steps along these lines will add 1 to the k term. But why is this so? Why should it be true? In this video, we shall attempt to answer this question and alleviate the pains of curious high schoolers worldwide. Now, remember that our main goal here is to prove that a relation exists, or doesn't, between the layers of the Pascal's triangle. So, let's do what many mathematicians and scientists do to explain the phenomena. Theorize. Let's start with a statement. Prove that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. I know this looks complicated, but let me make this clear. All this formula is trying to say is that the element in a row of the Pascal's triangle is the sum of the two numbers above. For example, if we set n equals to 5 and k equals to 3, then this basically says that 5 choose 3 is equal to 4 choose 2 plus 4 choose 3. We can verify this numerically. Notice how this rule applies here, 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 and everywhere else on the Pascal's triangle. This is how we know our formulation here is the step in the right direction. Now, I know that dealing with only letters can get intimidating. So, let's carry on with an example of n equals to 5 and k equals to 3. 5 choose 3 over here corresponds to choosing 3 objects from a group of 5 unique objects. So, let's say I have a bag of letters from A to E. 5 choose 3 would represent the number of ways to pick 3 letters from this 5, which in our case would be 10, shown here. Now, how can we visually verify that 5 choose 3 comes from 4 choose 2 and 4 choose 3, as our formula states? Well, let's zoom in on the plus sign here. When we have a plus sign in combinatorics, it's usually a telltale sign that we are splitting this set of 5 choose 3 ways to choose letters into disjoint subsets. This means that these groups do not overlap with one another.
For instance, if I want to figure out the number of ways to make a 4-digit PIN code with numbers from 0 to 9, the two disjoint groups I might consider making would be the odd PIN codes and the even PIN codes. These two groups will have no overlap with one another, and when we add odd and even together, we will get the total number of ways to make that 4-digit PIN code. Now that we understand the role of the plus sign in our formula, how exactly can we apply it to this set? How can we split this set into two disjoint groups? Pause the video for a second here and try to figure it out. Are we back yet? Here's the answer. Let's take a look at the proposed formula again. We notice that for both of our addends, we have a 4 choose something. This would signify that our approach to grouping these letters will only concern 4 of the 5 letters. So, let's zoom in on 4 of these letters. Now, we see that the addends are actually 4 choose 2 and 4 choose 3. Or, how many ways are there to pick 2 objects from 4? And, how many ways are there to pick 3 objects from 4? Look at these cases again. Is it clear how we can split these groupings now? Well, we see that these groups correspond to choosing 3 letters out of the 4, and these cases correspond to choosing 2 letters out of the 4. We now see that we have formed 2 disjoint groups that encompass all the combinations, and hence we are certain that we are on the right path. Now, how exactly can we characterize these 2 groups? How can we generalize this grouping? Well, we see that the 4 choose 3 group is characterized by the 5th element, in this case A, not being there. Meanwhile, the 4 choose 2 group is characterized by this A being here. And this is, in fact, the logic that we can apply to all valid values of n and k to prove this theorem. At this point, I think it's worth explaining that this proof will work regardless of which of the 5 letters we choose from. In the field, we see that this proof works without loss of generality. Now, let's say we have a bucket of n objects from O1 to On, and let's say we want to choose r objects from this. We can choose to do it like so. Case 1. These are the ways, without loss of generality, in which one of the objects, O1, is inside the combination. This means that we have to devote 1 slot for O1, and we have n-1 objects in the pool to fill up r-1 remaining slots. How many ways are there to do this? Well, there are n-1 choose r-1 ways. This is the first case. Case 2. These are the ways in which O1 is not inside the combination without loss of generality. Well, now we have r slots for n-1 objects, and there are n-1 choose r ways to do so. So, this covers all the possible ways of choosing r objects from n things. Hence, we can conclude that the number of ways is the sum of these 2 cases. And it just so happens that the total number of ways is simply n choose r. Hence, we can conclude that n choose r equals to n-1 choose r-1 plus n-1 choose r. Now, with all this mumbo jumbo about combinatorics, what does this mean for the Pascal triangle? Well, we can use this identity to construct it from the ground up. Let's start with 0 choose 0. To the left and right would be 0 choose -1 and 0 choose 1. These 2 numbers are just 0 because, well, last I checked, you can't choose 1 object from 0 objects. Neither can you choose -1 objects from 0 objects. Now, let's try the sum of the terms below. To the left would be 0 choose -1 plus 0 choose 0, which by the formula we just derived earlier will be 1 choose 0. To the right would be 0 choose 0 plus 0 choose 1, which, applying the formula again, is just 1 choose 1. We can apply the same formula for these grayed out terms, but I won't cover that now. From these 2 terms, we can do the same for the next layer, in which we have 2 choose r. and the next, and the next, and so on. Now, realize that what we've been doing is the basic property of the Pascal's triangle. When we add two adjacent terms, we get the term right below it, and we start at 1 at the very top. Therefore, it is no wonder that when we convert these NCRs into proper numbers, we get the Pascal's triangle. And this is why the Pascal's triangle can be written as a long string of combinatorics. It's cool, isn't it? And the implication of this is that we can use the Pascal's triangle to figure out the coefficients of the binomial theorem, since the coefficients are nothing more than combinatorial terms. This wraps up our two-part series on the good old binomial theorem. We hope that this series has let you gain a deeper appreciation of this seemingly esoteric theorem with so many twists and turns that are often left unanswered until many years after this formula was first introduced. If you do have any questions, feel free to ask them in the comments below. We'd love to explain any concepts that you don't understand. After all, who are we to burn the flames of a passionate soul? Thanks for watching, and see you in the next one.